Good morning, everyone. We'll be starting class in 1 to 2 minutes' time. Good morning, everyone, and the lectures that we're going to be focusing on today are going to be a continuation of the Z-transform lectures from Monday. In particular, what we're going to be focusing on would be how do we obtain the open form and closed form solutions of the Z-transform, as well as how can we use the Z-transform to solve difference equations, which are basically the discrete time version of differential equations instead. Afterwards, once we finish the materials for these lectures, we'll be moving on to the select questions to be done live for problem set 2A, and if time permits, also for problem set 2B. If for some instance we can't reach problem set 2B, we'll do those live questions on next week's Wednesday session, and we'll also focus a little more on a midterm sort of preparation, because your midterm is scheduled for the 3rd of March, which is next 2 Wednesdays. Alright, so let's get started with today's lecture. So there are some properties of the Z-transform that are quite similar to the Laplace transform. In particular, these properties, being these 8 properties listed here, share some sort of similarity with the Laplace transform, but whereas the only properties that are quite important to us would be the convolution property here, which is anything that is convolved in discretized time is a multiplication in the Z domain, as the same property holds true in reverse. Anything that is convolved in the Z domain is a multiplication back in discretized time. The other property that is going to be quite important to us is going to be the reflection property here, where if it's x of minus n, is going to be x of 1 divided by z. And the shifting property, where if it's x n minus n, is going to be z to the power of negative capital N of x of z. So these 3 properties in particular are what we're going to pay attention to. Excuse me for that. These 3 properties are what we're going to be paying attention to, in particular, how we're going to go about solving our Z-transform equations. And we'll see in particular for the shifting property, how do we go about solving the difference equations as well. So we need to compare a few properties between the Laplace domain and the Z domain, such that if we had the linearity property where we had x1 and t and x2 of t multiplied by some constant scalars a and b, these scalars do not transform, they just transfer across directly for the s counterparts as well. The same holds true for the Z transform, so any scalar properties that are multiplied by x1 kt and x2 kt are just directly transferred across into the Z domain as well. For the shifting property, if we had x of t minus t naught, this in the Laplace domain is going to be the exponent power to the minus s of t naught of x of z. In the Z domain, once we have some type of shifting, being that it's going to be x of kt minus nt multiplied by the unit step that is also shifted of the same property of nt, the Z domain equivalent is going to be z to the power of negative n, where negative n is going to be our shift multiplied by x of z. For scaling, in the Laplace domain, if we had x of at, that's going to be 1 divided by a, x of s divided by a. And in the Z domain, it's going to be a to the power k of x of kt, and that transfers to x of z divided by a. If we have a multiplication by t of x of t here in the Laplace domain, that's going to be a negative differential of x of s with respect to ds. This property is also similar to the same thing as Laplace domain in the Z domain. We had some k x of kt here, it's just going to be minus z multiplied by the differential of z x of z with respect to z. So there are a few similarities between the transforms. It doesn't mean you have to go and learn off all of them in particular. So certain similarities here we're going to be taking advantage of, and how we can use these similarities to go about solving for our Z transform in particular. So if we backtrack a little bit, we watch back our discrete time Fourier transform equation for any discretized time sequence x of n. We know that the equation is going to be x of capital omega given here in this green shaded block. The question now is going to be, what's going to be the Z transform of this sequence x of n? And as such, the x of z equation shares a very similar form to that of the Dtft sequence, where the only difference is that the exponent form here is just replaced by z to the power negative n. So the question here is going to be, when is the Dtft equal to the Z transform? So if we let z here equal to e to the power j capital omega, and the reason for this being, when is this property held true? This property is held true on the unit circle itself. So for the entire unit circle of radius 1, the circumference of the circle is where z is equal to e to the power j capital omega. As such, when you evaluate the Dtft of x of n, it comes like you're evaluating the circumference here of this unit circle in the respective Z transform. Now, one thing to note is that if our region of convergence does not include the unit circle, then when you try to do the Dtft of x of n, there will be no convergence. So, as such, the Dtft of x of n will not exist. So, for our previous example here, where we did a general Z transform of a discretized time sequence, and we had z divided by z minus alpha, and we said magnitude of z is going to be less than magnitude of alpha when we calculate for the region of convergence. This will not have a Dtft if the alpha here is going to be less than 1. So alpha needs to be greater than or equal to 1 in order for the x of n sequence here to have a Dtft sequence. Now it's possible for us to express the Z transform in the following polynomial form, where we have the maximum power of Z possible down to the minimum power of Z possible. So we have it in descending order of powers of Z. Or in a very familiar form, which is going to be our poles and zeros form, where we have all the zeros on the numerator and all the poles on the denominator. And the zero pole form or the pole zero form is also useful for performing and evaluating pole zero plots in the Z-plane. Now, discretized time systems basically have different ways they can be represented. We can use them by transfer functions, which is going to be the output divided by the input in terms of Z. Impulse responses, which is like if we have an h of n sequence equal to a Z delay of h of Z. Most of the times we won't really use the impulse response. And difference equations, which are given by some form of y of n, and then a y n minus 1 and n minus 2 and so forth. And similarly with x of n minus 1 and n minus 2 and so forth. The difference equation form here is basically the discretized time version of differential equations. And we'll be looking at difference equations in the next lecture and how we can go about solving them in particular. So if we're given any generic y of z sequence here, in its transfer function form, and we can basically say this is y of z divided by x of z, where x of z is 1. The general question is, how do we get back to y of nt, and what does this output sequence look like? So that means we need to find the inverse z transform, and this can be done in one of 3 ways. We can do long division, which will give us the open form solution, or the infinite solution. We can do complex integration, which we will never do because, as its name said, it's complex. And we can do partial fractions and tables, which will give us the closed form solution or the finite solution. So just to reiterate, long division will give us the long division will give us the open form solution or infinite solution, because as its name suggests, long division means for when we divide up these sequences, they do not have a remainder of 0, they just keep on going towards infinity. We can do complex integration, but we will not do this, we will briefly discuss this, because as its name said, it is complex in nature. And we can also do partial fractions and tables, which will give us the closed form solution or the finite solution. So we look at each one of these in turn. So for long division, it basically means you need to divide the numerator by the denominator up to a certain term when you're evaluating the quotients in the long division formula. So if we expanded out our y of z equation and we have it from in descending powers of z here. So in this case, it will be increasing powers of z to the negative 1, but that means we just have to have it with z to the 0 here, then z to the negative 1, and z to the negative 2, and so forth. We can perform long division, and we can get the y of z sequence here. So I'm going to do this long division for you guys on the whiteboard, so you can see step by step how we can go about doing this. So in our slide here, remember we'd be dividing the numerator by the denominator. So when we're setting up our long division, so our long division table here, we'll put the numerator in this part here, 1.4 divided by 0.6 into 1 plus 0.2, that's to the negative 2. And we'll put our denominator here on the outside. 1 minus 1.1, that's a negative 1, plus 0.08, that's a negative 2, plus 0.02, that's a negative 3. And I'll just verify that on my side. Lecture 1. 1.4, negative 6.2. Alright, nice. So remember, when we start doing this long division in particular, it's important that we have the numerator and the denominator in descending powers of z. So as we can see here in particular, for my numerator, I had z to the 0 first, then z to the negative 1, and then z to the negative 2. And then for my denominator term, I had z to the 0, and z to the negative 1, z to the negative 2, and z to the negative 3 here. So when we start our long division, we're only be concerning ourselves with the first terms here for the numerator and the denominator. And then we will see how we go about calculating for our long division terms in particular. So we say here for the numerator, which is 1.4 for its first term, we're going to divide this by the first term of the denominator here, which is 1. So the result we get here is just going to be 1.4. We then take this result here, and we're going to multiply this result by each one of these terms on the denominator. So in particular, 1.4 here is going to be multiplied by 1, which is going to give us a result of 1.4. 1.4 here is going to multiply by negative 1.1 z to the negative 1. And if we do that multiplication, this will give us minus 1.54 z to the negative 1. 1.4 here is going to multiply by 0.08 z to the negative 2, which is going to give us a result positive 0.112 z to the negative 2. And then 1.4 here is going to multiply by 0.02 z to the negative 3, which is going to give us, let's just this out a little bit, right? Plus 0.028 z to the minus 3. Now, these two terms here, these two equations that we have being this here, the numerator, and then our calculated result from the result of the division that we just did, these two lines here need to subtract one another. So we're going to put a minus sign here. And then we're going to calculate what's going to be our remainder from this. So 1.4 minus 1.4, that's just going to be 0. Then we have negative 0.6 here, minus negative 1.54. So that's going to be negative 0.6 plus 1.54, which was going to give us a result of 0.94 z to the minus 1. For our z to the negative 2 terms, this is going to be 0.2 minus 0.112, which is going to give us a result of plus 0.088 z to the minus 2. Just erase that. Just look at a little neater. And then there's no z to the negative 3 term on top here. So that's going to be 0 minus 0.028 z to the negative 3. So that's just going to be minus 0.028 z to the minus 3. So now that we have our remainder term here, we can continue our long division as of such by using the first term of the remainder and divide it by the first term of the denominator and continue our division up to a certain term. So I'm just going to continue division up to the z to the minus 2 term here as the quotient result of our long division. So for our next step here, we're taking the first term of the remainder and we're going to divide it by the first term of the denominator here. That's 0.94 z to the negative 1 divided by 1. So our quotient result is going to be 0.94 z to the minus 1. And then we just repeat the steps that we just did from before our first division step. So we just take this first term here, 0.94 z to the negative 1, and we multiply by each one of these terms here on the denominator. So doing so, let's go ahead and see what we get. So 0.94 here by 1 is going to be 0.94 z to the negative 1. Right, 0.94 z to the negative 1 by 1. Going to give us 0.94 z to the negative 1. Then we do this term here, multiply by negative 1.1 z to the negative 1. And that's going to give us positive. Sorry, not positive. It's going to be negative. Minus 1.034 z to the minus 2. Then we take this term here as well, multiply by 0.08 z to the minus 2. That's going to give us positive 0.0118 z to the minus 3. And then we take 0.94 here, multiplied by 0.02 z to the negative 3. So calculate that very quickly. 0.94 by 0.02. So this here is going to be that. Well, I'm just running back through my calculations here. Yeah, so the first thing we consider when we're doing the division. So I'm just running back my calculations here just to make sure my division steps were correct. Right, so that. 0.51, correct. 0.94 by 0.08. Alright, okay. So, oops. Right. So, made a mistake here for this one. Alright. So, we do 0.094, sorry, 0.94 z to the negative 1 by 0.08 z to the negative 2, which gives us a result of 0.0752 z to the minus 3. And then 0.94 plus 0.02 z to the negative 3. When we multiply these two, this part here is going to be plus 0.0118 of z to the minus 4. Right? So that's what it's supposed to be. So hold on. Correct my solutions here as well, just to make sure it matches up. Oh. That's right. Fine. Okay, good. And then we just do the same subtraction from before. So these 0.94s here, they're going to just result in 0. We have 0.088 z to the minus 2 here, minus negative 1.034. That's going to be a positive, so that's going to be 0.088 plus 1.034, which is going to give us 1.122 z to the negative 2. 1.122 z to the minus 2. Then we have, for the z to the minus 3 terms here, we have minus 0.028 minus 0.0752. So we calculate that out, 0.028 minus 0.0752. We get minus 0.0472. Oops. 472 z to the minus 3. And then we have for z to the negative 4 term, there isn't one existing here, so that's going to be 0 minus 0.0118, so that's going to be minus 0.0118 z to the minus 4 here. Right, so let me just correct my solutions here as well, because I'm going to upload these later on as supplemental notes. 0.0118 to the power later. Alright, good. And then our last step here, because we're just going to be stopping at z to the minus 2 on our quotient, is that we just basically say this 1.122 z to the negative 2 here being our remainder is now going to divide by the first term here in our denominator. So our result here is just going to be 1.122 of z to the negative 2. And because we know that for our open form solution we stop at this z to the negative 2 term here, we don't need to do any more long division. So we can basically stop our work in here at this point, because we have the required quotient as our result. So if we need to write this out, in particular, back into y of z equation, because we did long division, this here is going to be y of z. We put our quotient as is, which is going to be 1.4 plus 0.94 z to the minus 1 plus 1.122 z to the minus 2 plus, and then we have our remainder here that needs to be divided by our original denominator. So that's going to be 1.122 z to the minus 2 minus 0.047 z to the minus 3 minus 0.0118 z to the minus 4. And this here being our remainder needs to divide by our original denominator a little bit. So this here is going to be 1 minus 1.1 z to the minus 1 plus 0.08 z to the minus 2 plus 0.02 z to the minus 3. I remember the reason why this is because we have our result here on the top being our quotient, which is the result of our division, and the remainder here still exists, and this remainder divides by the original denominator as a result of the long division process. Alright, so if you do encounter a question that asks you for the open form solution or the infinite solution of a y of z equation, you're going to have to require to do long division, and the question will basically tell you up to which term to stop. So they might tell you, okay, obtain the open form solution up to the z to the minus 2 term or up to the z to the negative 3 term. That means on your quotient here for your division, in the result of the division, you need to get up to the z to the negative 2 term here or up to the z to the negative 3 term here by continuing division as is. And then when you're writing up the y of z equation, the quotient here is just going to be as is, but the remainder that you do still have here is going to be divided by the original denominator terms that you had here. There will be some rare cases when you do the long division process and you do get a remainder of 0. In such a case, when you do get a remainder of 0, your solution is no longer open form. Your solution becomes a closed form solution, because that means you can't continue the division. The division is finished. So your solution converges because of a remainder of 0. As of such, your solution is no longer an open form solution, it is a closed form solution. So that is a very rare case that actually happen when you are doing long division. So just take note of that rare case in particular. Right, so let's bring this back down here and let's continue from where we were. right? So we basically can see here that after we did our long division processes here, we got the result as seen here on the slide. And to transfer this back from y of z here into y of nt, we just focus only on the quotient result that we obtain. So each one of these values here can be immediately transformed using the shifting property of the z transform. So as of such, when we do this shifting property of the z transform here, every term here is just going to be a delay with respect to delta n of t. So this 1.4 here is just going to be delta of n of t. This 0.94, which was z to the negative 1, is just going to be 0.94 delta of n minus 1t. And for this z to the negative 2 term, that's going to be delta of n minus 2t, where the term in front of the z to the negative 2 is just going to transfer here accordingly as of such. So what this does look like is just a sequence of values of each one of these terms for the z components, and it's just basically just a one-dimensional vector that can just be plotted accordingly for each n term as of such. So the working for the open form solution or the infinite solution is really in the long division process. And once you do have your quotient being your result, you can just transfer that immediately using the shifting property of the z transform to actually obtain the open form solution as required. So this here is going to be the easy part once you do have the quotient. All right. So are there any particular questions regarding the long division process for the open form or infinite form solution of the z transform? Oh, for this graph, so the y-axis here is going to be y of nt, and the x-axis here is just going to be n. So once you're doing the open form solution in particular, the remainder part of the y of nt form won't be applicable once you transfer it back into, the remainder part of the y of z form won't be applicable when you transfer it across into the y of nt form. And that being is that such that, remember, the question was basically asking you to just obtain up to a certain z component before you actually do the transform. So the question will be structured such that find the open form solution of the following y of z equation up to the z to the negative 2 term, and as a result, once we do the long division process and we get our quotient up to that z to the negative 2 term, the remainder is just going to be represented by this plus dot 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 plus here for our y of nt. But the important part here is just going to be the quotient results that we did obtain from the long division. On the y-axis here for the graph is going to be y of nt, and on the x-axis here for the graph is going to be n. So let me just write that in on the slide itself. This here is going to be y nt. This axis here is going to be n. Alright, doesn't look like we have any more further questions regarding the long division process. So let's go on to the next way to go about solving Z transform equations. So in commenting on the long division process, it just basically gives you the direct sequence of values to produce the transfer function. Once the sequence doesn't end, meaning that you don't get a remainder of 0, this is referred to as the infinite form or the open form solution. It's also referred to as an infinite response. If you do happen to get a remainder of 0, meaning that the sequence itself ends or converges to some value after some finite number of values while you're doing the long division process, it becomes a finite solution or a finite response, also referred to as a closed form solution. And finite responses can actually be directly programmed into a computer by just entering the vector, the one-dimensional vector of these numbers, because the sequence actually does have an end. So the next technique that can be used for solving Z transforms is referred to as complex integration, which is given by this surface integral equation here in terms of Z, referred to also as a contour integral. The technique used to evaluate it is known as the method of residues. If anyone actually wants to go and look up how to evaluate this or how it actually works and so forth. But for the purpose of this course, we will not be doing complex integration. The last way to go about solving for Z transform is a familiar way that we've been using since for the Laplace transform, which is basically partial fractions and then just using the Z transform table to get it back in terms of y of nt. Like I said, this is referred to as the finite solution or the closed form solution method for solving a Z transform. So we just need to make sure that once we do have our Z transform equation, we factorize it and then evaluate it in partial fractions, and then we just use the Z transform table to find the inverse. And that gives us the closed form representation y of nt. We're going to examine this on our example equation that we just not had before. Now, there's one thing to note before you actually do perform partial fractions, is that for partial fractions to occur, the degree of the numerator here must be less than the degree of the denominator. If this condition is not satisfied, you need to keep on dividing this equation until you get the remainder here satisfying this condition. And then you perform partial fractions on the remainder, and then you can do the inverse Z transform accordingly. So for our example here, so you'll see an instance in the next lecture where we actually do this to satisfy the condition. But for now, we're just going to return to our general example for solving using partial fractions and the inverse Z transform table. So for our example here, we already factorized the denominator as is. So we're going to treat Z to the -1 here as a variable. So for some people who do have visual conception problems, I know I do have it sometimes, we basically do a substitution here. So we just like let x equals Z to the -1, means x squared is Z to the -2. and x cubed here will just be z to the minus 3 accordingly, and so forth. And as a result, I can just transform that entire equation there from y of z into y of x. If I don't want to use x, I can just be like, okay, instead of using x here, I can be like, let just this be equal to some other term, being like, let's say m is a pointer on. Say m, and we say m squared and m cubed. So I can just transform that from y of z into y of m. I will just be dealing with positive powers only, which makes my life a lot easier than for factorization and obtaining partial fractions and so forth. Alright. Okay, so give me 1 second. I have to deal with something here. I'll be back in 2 minutes. Alright, sorry about that, guys. Alright, so let's continue where we left off. So, remember when we're doing our partial fractions here, we need to treat z to the negative 1 here as our variable. Not z to the negative 1. So, for people who do have some visual conceptual problems, when you're doing the factorization process for this, or for doing the partial fractions themselves, you can just use a substitute variable here and let m equals z to the minus 1. So as such, if it's z to the negative 2, that's going to be m squared, and z to the negative 3 is going to be m cubed, and you can just transform this from y of z into y of m accordingly. And then when it's time to do the inverse, you just go back in terms of z, and then you use the transform table to get to your y of nt formula as required. So if we treat z to the negative 1 here as our variable, and well, you can do the substitution, but for our example here, we're just going to be treating it in terms of z here, we can express y of z here into our partial fraction coefficients for each one of these factors on the denominator. So because there are 3 factors, there are going to be 3 coefficients that we're going to calculate for, which is going to be a, b, and c for each one of these. And then we can evaluate for a, b, and c such that we can use the optimized version for solving for partial fractions here to obtain our results for each one. So for a here, we use the numerator from y of z, and then we use the other 2 denominator terms that's not associated with a, and we put these 2 on the denominator here to multiply with each other. And then because this is in terms of z here, we need to substitute in a z value. So we watch the term of a here for 1 minus z to the negative 1 in the denominator, and we say, okay, let 1 minus z to the negative 1 here equal to 0, and as such we get z to the negative 1 here is going to be equal to a value of 1. So we substitute that value of z to the minus 1 equals 1 into this equation here for solving for a. And as a result, we can get our result for our a value here accordingly. So this method, which we use for solving partial fractions, is effective when all these terms on the denominator here are not repeated. So these need to be independent and unique terms on the denominator when you're solving for partial fractions. If for some reason you do end up with a repeated term, like if it was 1 to the minus 1, z to the negative 1, then this one here was also 1 minus z to the negative 1, and so forth. The partial fractions themselves are going to take on a completely different form, and that means you're going to use the manual evaluation method to solve for your coefficients as required. So it's important to know and review the different forms of partial fractions that are required once you start encountering repeated roots and different types of roots accordingly as of such, because that means the partial fraction evaluation is going to be different than what you're seeing here in these slides. So make sure and review those in particular. So the method I just explained here works as an optimized version for solving for a, b, and c, because each one of these denominators are unique in nature. So similarly, if we try to solve for b, use the numerator of the y of z equation that we had before. And then for b here, we use the other denominator terms that are not associated with b, and we put this on the denominator here for solving for b. So that's going to be 1 minus z to the negative 1 here, and 1 plus 0.1 z to the negative 1. We multiply those 2 here on the denominator. And then for z to the negative 1, the value that we need to substitute here for solving for b, we let 1 minus 0.2 z to the negative 1 here, which is the denominator term associated with b, equal to 0, and we solve for z to the negative 1. So as such, we get a result of 5, and we substitute in this value here into this equation to solve for b as a result. And similarly, we can do the same thing for c as well. It's just basically the same method that we do to solve for the a, b, and c. So once we do have our terms for a, b, and c, and we put them back into our y of z equation, the next step here is to check the z transform table to see, okay, how do we go about solving for y of nt? Now, in some cases, you may encounter a z transform table that has positive powers of z. And in this particular case, that we can see here on the lecture slide. But that's nothing to be worried about in particular, because this comes like we just say, okay, for this z, divided by z minus 1. I'm going to write it out here. If we wish to transform this back into negative powers of z, we just multiply by z to the minus 1 here on the numerator, and z to the minus 1 in the denominator. As a result, this will just become 1 divided by 1 minus z to the negative 1, which we can see here in our blue shaded block. Similarly, for z minus alpha, z divided by z minus alpha, we can do the same thing. And we get a result of 1 divided by 1 minus alpha z to the negative 1. So depending on the z transform table that's given to you, it may be expressed in positive powers of z or negative powers of z. That's nothing to be worried about. You can just re-rationalize the terms accordingly by multiplying by z on the numerator and the denominator, or z to the negative 1 on the numerator and denominator accordingly, to get the associated transform equivalents in positive powers of z or negative powers of z. Once we do have the associated transform equivalents, we just map it back accordingly to which terms they're associated with in the z transform table. So for our first term here, which is 1 minus z to the negative 1, when we did this transform, we see here that this transforms to the u of n. And then for our second and third terms here, which is 1 minus alpha of z to the negative 1, which maps back to this term here, we can see that this second and third term here can map back accordingly as such. Now, some people might be like, okay, well, this is 1 plus 0.1 z to the negative 1. Yes, it is that. But to map it back to our transform here, we can just rewrite the equation very simply, such that this will just become 1 minus 0.1 z to the negative 1. And this here satisfies that form. So there's nothing to worry about if you have a 1 plus alpha. It's just basically you can just put 1 minus and then in brackets minus that alpha of z to the negative 1. And that won't be an issue at all. So now that we have the terms mapped to our z transform equivalents to get back in terms of y of nt, we can just use the z transform table accordingly, and we can solve for y of nt here. So our first term was just a unit step. Our second term here, because this was alpha n to the u of n, we have minus 0.567 here. Our alpha term here is going to be 0.2. So minus 0.567, alpha term is 0.2 of n, u of nt. And then for the third part here, our constant was 0.83. Our alpha term was negative 0.1, and that's just going to be u of nt here. Alright, that brings us to the end of our Z Transform 2 lecture, and to the end of how we go about solving for the closed form solution or the finite solution of the Z transform. So are there any particular questions associated with the material of this lecture? No, yeah, sure. So let's backtrack a little bit. Alright, so we got A and B here for comparison, right? So when we're solving for A here, remember we had our y of z equation in this form here to begin with. And then we said this here was basically the same as A divided by that, B divided by that, C divided by that. So that basically means here that when you're doing this, you need to keep this numerator term here constant when you're evaluating. So that's why we have this numerator term here constant when we're solving for A. And then for the other terms that's going to be on the denominator, that's going to be the terms here that are not associated with A. So that's why you have 1 minus 0.2 here, multiplied by 1 plus 0.1, z to the negative 1. Now this equation here is in terms of z, and we need to figure out, okay, what's going to be the value of z to the minus 1 that we need to substitute to solve for a. So because we're solving for a here, the denominator term that was associated with a was 1 minus z to the negative 1. So we take that 1 minus z to the negative 1 term here, because we're solving for a. We say, okay, 1 minus z to the minus 1 here is equal to 0. And as a result, minus z to the negative 1 is negative 1, so that means z to the minus 1 here is just going to be 1. And we use this term here, where z to the minus 1 is equal to 1, and we substitute that there into our equation when we're solving for that. As a result, when we substitute that value here into a resultant equation, we can solve for a accordingly. So there are two steps in doing this. You need to formulate the equation first in terms of z to the minus 1. So because we're solving for a, we keep the numerator term that we had from before for y of z, and we associate the other denominator terms that are not associated with a, and we put this for a denominator here. So that's going to be 1 minus 0.2 and 1 plus 0.1 here, which is going to be a multiplication of the two. Because this equation here is in terms of z, in order to solve for a, we need to substitute a z to the minus 1 value accordingly. So because we're solving for a, we watch a denominator term associated with a here, which is going to be 1 minus z to the negative 1, and we say, okay, let that equal to 0, and we solve for z to the minus 1. So we did the work in here, and we see z to the minus 1 here is equal to 1. And then we substitute this value here into our equation, solve for a accordingly. And we did the same method here for b as well. In this case, the denominator terms are not associated with b was this 1 minus z to the negative 1 and 1 plus 0.1 z to the negative 1. And we then, to figure out what's going to be the value of z to the minus 1 here to substitute in for b, we just let 1 minus 0.2 z to the negative 1. I'm going to do the work in here for you. So we're going to be solving for b here. So we say 1 minus 0.2 z to the minus 1 is equal to 0. So 0.2 z to the minus 1, z to the minus 1 here, 1 divided by 0.2, 5. And then we just substitute that in here. And that's how we're able to solve for b as well. I'll review the long division example that I did just to make sure it was correct, because I do need to put up a supplemental note showing the steps how we went about doing the long division. So if I did it wrong, the supplemental note will have the corrected version. If I did correct, it will still have the correct version inside the supplemental note, so don't worry about it too much. Like I said, the supplemental note itself will have the correct form as required. Alright, any further questions? I think I see what the guy was one of your colleagues was saying with the remainder for the long division. Alright, so I could calculate that out one time. I gave you the corrected version. I probably didn't complete the multiplication like you said. So that's 1.1. Alright, yeah. See what he's talking about. Okay. So, okay. So, let me correct that immediately with the long division process here, which we just now did. So, your colleague pointed out that these terms is wrong. He was right on this. These terms here were wrong because I was correcting my solution as I was going. So I'm now going to go on to write on. I'm going to write the correct version here. That's one. So this could be minus 1.232. That's a minus 3. And then here we have 1.122 multiplied 8. Right. 8 minus 3 minus 4 positive here 1.1 0.4 then 5. Alright, yeah. Okay, so that's supposed to be the correct remainder. Remainder here is going to be minus 2, 3, 8, and minus. Right, yeah, so that's supposed to be the corrected version for the long division. Because I was correcting my solutions, I just keep on going. Thanks for pointing that out. I'll make sure and correct my solutions here now to match accordingly. So once I put up the supplemental notes, it'll be the correct thing. 4 plus 0. Alright, nice. So my supplemental note is corrected, so once I put that up, it's going to be the correct thing. So thanks for pointing that out. Alright, so there shouldn't be any more questions here accordingly. Alright, so let's move on to the next lecture. This. So back to 13 here. Alright. So lecture 13 here, which is going to be the last Z transform lecture that we're going to be doing, is going to focus more on how do we go about solving difference equations, which are basically the discretized form version of differential equations that were represented in continuous time. And in particular, we saw in Monday's lecture the reason why do we need the Z transform, because the Laplace transform itself doesn't work well with discretized time signals. So as of such, if we want to have some sort of differential form in discretized time, we need to have its own form, which is referred to as the difference equations. So we want to see why we use difference equations here, and as well as how do we use the Z transform to solve for these difference equations in particular. All right, let's go. So any discretized time system you're going to be dealing with, it's going to be using difference equations here to represent its behavior. So just to backtrack a little bit, if we had an x of n going into a system of h of n to produce a y of n, where we had some impulse response being formulated here, basically because we're dealing with a sequence of numbers, and the step response and the system response and the system output is also going to be a sequence of numbers, we're going to have to use a differential equation equivalent of the continuous time to represent this in discretized time, which is going to be difference equations, which is required to represent the behavior of our system. So in evaluating how do we formulate this difference equation, we're going to have to go back to differentiation by first principles here. So let's say we had a y of t value here that occurred at t, and then a y of t plus delta of t value here occurring at t plus delta of t, where delta of t here is going to be a really small difference in time. And doing the differential, which is basically the gradient, is just going to be the difference between these two coordinates here. So the numerator will be the difference in terms of y, which is y of t plus delta of t minus y of t. And the denominator here is going to be a difference in x, which is t plus delta of t minus t. So because we're doing differentiation by first principles, that means we also need to do a limit evaluation here, because we're saying delta of t here is a very small change. So we say because it's a very small change, that limit of delta of t is going to evaluate towards 0. So this here gives us the formulation of differentiation by first principles, where delta of t here is a very small change in time. If we switch this accordingly, such that instead of this being delta of t, we now sample y of t at every t seconds, meaning that we discretize our signal. When we rewrite our equation for the differential, the difference in y values here is just going to be y of n plus 1 and y of n. And the difference in x values here is going to be just t, which is n plus 1t minus n of t, which we're just going to say the result of t. So therefore, for any differential equation that we had in continuous time, the discretized time version is just going to be where we substitute in those first principles accordingly. So y of t will just transfer to y of n, x of t will transfer to x of n, and dy dt just transfers to the discretized form version that we just saw in the previous slide. And because everything here now is in terms of n and just t, and there's no dt or dy accordingly, this is what we refer to as the difference equation, because we're using this for our discretized version of that continuous time signal instead. So we can rearrange that difference equation that we have here, and we can get it in terms of y of n plus 1 and have x of n and y of n onto the right hand side here. Typically, if you're trying to solve this, because this y of n plus 1 term occurs one instance more than the x of n and the y of n terms, this means normally you'll have to use some sort of recursive technique to solve it, meaning that you need to obtain y of 1, and then you have to get y of 2 and substitute for 0 and 1 here, and then 3 for 1, 0, 1, 2, and so forth, which is a very tedious process, and especially when you're trying to solve for higher and higher values of n. So that means we're going to have to figure out another way to go about solving this. Now visually, when we do the derivative of this continuous time signal that we have here, we can see here that the original sequence, if we discretize it, these are given by the blue blocks here. And we do the differentials accordingly. We basically see for each differential point here where there's no change, it's just going to be a very small, it's literally going to be at the 0 value point here. And then we have very small changes. Once these changes are constant, they're going to rise here a little bit and so forth. But when we do have a huge change in gradient, then see the differentials here with a map accordingly representing each one of these huge changes. So it's possible for watching any general linear constant coefficient difference equation, meaning any general difference equation that you want to have, we can map all the y terms onto the left hand side and all the x terms onto the right hand side, because y terms are generally outputs, x terms are generally inputs. And once we have this formulation mapping, we get able to actually program a difference equation into a discrete time system because of this equation mapping. So the important things to note is that when you're trying to solve for these difference equations, we're basically going to end up using the Z transform. And in using the Z transform, that means we need to figure out how do we cater for each delay property that we just now saw here. So like we'll have a y of n here. Yes, that transforms to a y of z. But then we have a y of n minus 1, and then we might have a y of n minus 2. Similarly, we'll have an x of n minus 1 and x of n minus 2. So what's going to be the equivalent Z transform to each one of these delays? That's going to be the question that we have to answer. So it's possible to use the delay property and the shifting properties here of the Z transform to map to these different equations accordingly for each one of these delays. So the general form here for any delay of samples is given by x of kt minus nt in this equation form here. And it's a little bit complex to notice at first, but we're going to take it for a first delay and the second delay, and we can see how the equation itself will expand out accordingly. So for when we have a delay of 1, being that it's going to be x of kt minus t or x of n minus 1, the equivalent transform for this is going to be z to the negative 1 of x of z plus x of minus 1. And this x of minus 1 here is going to be a constant, which is going to be given to you at the start of the problem. Similarly, for a delay of 2, which is going to be x of kt minus 2t of x, or x of n minus 2, we see here that the equation here expands out to accommodate for this minus 2 accordingly. So now this becomes z to the negative 2 x of z plus z to the negative 1 x of negative 1 plus x of negative 2. X of negative 1 here and x of negative 2 are constants which are going to be given to you in general. So we can see here that this expansion has some sort of pattern that keeps on going. So let's say if I wanted to formulate an equation for, let's say, x of n minus 3 to get our equivalent Z transform, that means it's going to be z to the minus 3 of x of z plus z to the minus 2 of x of minus 1 plus z to the minus 1 x minus 2 plus x of minus 3. So we basically can see that it's easy enough to formulate the pattern when we're trying to evaluate for higher delays in particular. And all those stem from this general form of the x of kt minus nt equation that we had. So in using the Z transform to solve for these different equations, that's going to be the purpose of today's lecture. So let's say if we had an example difference equation here in terms of y and x with delays of 1 and 2 accordingly, and we're going to figure out, okay, what's going to be our transfer function in terms of z for this difference equation. So in using the transfer function delay property that we just now observed, it's possible for us to obtain this equation as required. So y of n here will transfer to y of z. The negative 0.5 is a constant, so we hold that on the outside here. Y of n minus 1 is going to transfer to z to the negative 1 y of z plus y of negative 1. Y of n minus 2 here is going to transfer to z to the negative 2 y of z plus z to the negative 1 y of minus 1 plus y of minus 2. And similarly, we can do the same things for x of n minus 1 here and x minus 2 here accordingly, by just keeping the constant terms here on the outside, because, like I said, constants don't transform, they just directly transfer across. So if we ignore those initial conditions there, such that y of minus 1 and y of minus 2 is also equivalent to x of minus 1 and x of minus 2 equal to 0, we can resolve the equation here into this very simplified version. So just remember, typically we do give values for y of minus 1 and y of minus 2 because these are output values as required. And in some cases, we do give you the values of x of minus 1 and x of minus 2. Now, there may be a case where you see that we give you values for y of my negative 1 and y of negative 2, and we say x of kt is equal to u of kt. And because this is u of kt being the unit step, that means an equivalent Z transform to the unit step is going to exist. So that means we're able to transform x of kt into x of z. Because this is a unit step, that means x of negative 1 and x of negative 2 is going to be automatically be 0. Because we drop the unit step in terms of n, and this axis here is going to be n minus 1 and minus 2 here. These values here are just going to be 0. But then at 0, it's going to be 1, 1, 1 here, 1, and 2 for values of n. So this comes like if this was x of n or x of kt. So just by drawing out the unit step, x of minus 1 here is just going to be 0. And the same thing, x of minus 2 here is going to be 0 accordingly as well. So if you do encounter an x of kt equal to u of kt while doing these difference equations, just remember to use the z transform table to get the x of z, and anything that's going to be x of negative values is going to be 0 because of the nature of the unit step that you just now observed. So once we have this equation here, y and x, we just factorize out all the y terms and factorize out all the x terms, and we get it into its transfer function form, which is going to be y divided by x here. Now, we typically don't ask you the questions to get the frequency response, but I'm just showing you guys the illustration of what the frequency response will look like for this. If you do need to evaluate the frequency response, and like I said, typically we don't ask this, but let's say if you are using the Z transform later on for some application, to evaluate the frequency response, you need to let Z equal to e to the j capital omega, which is basically comes like if you're trying to evaluate the Dtft of this Z sequence here, which we saw in the previous lecture. And then you basically plot this in accordance with capital omega, which is going to be the frequency, so you can get your frequency response as required for the magnitude and the phase. This is also similar to that if you have the Z transform. It's also possible to get an associated mode plot for the Z transform as well by using the required command in MATLAB, which I can't remember right now, but I will try to figure out what the command is later on to tell you guys. So a question may be, what are the poles for this system that you just now evaluated? Because you know you have the transfer function here in terms of y and x. So that means that we just evaluate the denominator here being equal to 0, and we factorize this accordingly in terms of z. And we can see here from the factorized terms here, means z equal to 0.2 and z equal to 0.3. Because these terms here are less than 1, the system here is stable because they're within the unit circle. So that basically means like if we put the poles here represented by the x's, that's 0.2 and 0.3, and this dotted circle here is a unit circle. Because these poles here lie within the unit circle, our system is stable. If one of these poles were on the outside of the unit circle, that means the system itself is unstable. Alright, so backtracking, so what's going to be the solution for this difference equations? There's going to be two solution forms, which is going to be the power series form or the closed form solution. And both of these will start with the discrete time transfer function that we just obtained. So the power series solution, which is also the same thing as our infinite solution and our open form solution, is just basically we're just going to be dividing the numerator by the denominator to get the same sort of open form or infinite solution that we just obtained in our previous lecture. And then you can just use the h of n. To obtain h of n, we just use the delay property to transfer it back accordingly into its delta equivalence, which we saw in the previous lecture. So in evaluating this, if we divide the numerator by the denominator here, we basically can get our h of z and by this equation here. And we can then apply the delay property such that for z to the -1, this is going to be delta of n minus 1. For z to the -2, that's delta of n minus 2. And for z to the -3, that's going to be delta of n minus 3, where all the constants here just directly transfer. So if we plot the impulse response of this, because we can see here that we have an initial curve and then it just decays towards 0, and doing the power series form here that we just now observed, obtaining the open form solution or the infinite solution, this impulse response of this is what we refer to as our finite impulse response, which is also useful for creating something referred to as an FIR filter, an impulse response filter, which is going to be important for when we're going to be doing filter design in a couple of lectures later along in this course. Similarly, if we went about doing the closed form solution, we have to see here that the transfer function here is not proper because we're treating z to the minus 1 here as our variable. So because we have z to the minus 1 as our variable here, and that means we have z to the minus 2 here being matched, the degree of the numerator here needs to be less than that of the degree of the denominator before we do any partial fractions on it accordingly. So I'm just going to write this out to explain what I'm saying. So this comes like the same thing if we say that m equals z to the minus 1. So that means h of m here now becomes 0.6 m plus 0.3 m squared divided by 1 minus 0.5 m plus 0.6 m squared. And because the degree of the numerator here being m squared is the same as the degree of the denominator here being m squared, we cannot perform partial fractions. So we need to long divide until we do satisfy this condition accordingly, and the remainder in the long division. So if we long divide this equation here once, we can get the equation as it is here. But there's one trick to doing this long division before we go about doing this. So the trick in doing this long division is because we have this in terms of h of m, we need to arrange the division such that we go in descending powers of m. So when you're arranging the division here, you need to make sure that the division goes in descending powers of m such that, now I'm just going to set up the division table for you here. It's going to be 0.06 m squared. Oh, oops, this is too much onto the right space. So when you set up the division table here, you need to make sure that the denominator and the numerator are in descending powers of m because of this. Plus 1, and then you have 0.3 m squared plus 0.6 m. So if we did our initial division here, which is 0.3 m squared here divided by 0.06 m squared, we see here when we do that division, we get a result of 5, which matches back to our result of 5 here for our quotient. And then the remainder, when we do evaluate it, we'll get 3.1 minus 5 here accordingly for this in terms of m, and then we can transfer it back in terms of z if required, or we can still operate in terms of m and then do our partial fractions and then go about solving the equation itself in terms of z afterwards. So either way how you go about approaching it is fine, but just remember, once we do encounter this h of z here and you see that the z to the minus, whatever the z to the minus terms is on the numerator is more than that of the degree of the denominator, you need to make sure that you divide this out accordingly until you satisfy the condition for partial fractions, and then you use the remainder here divided by the original denominator and perform partial fractions on this remainder here only. The quickest way to see if this condition is satisfied, you let z to the minus 1 here equal to some constant. So the purpose for this long division here is that we see here that the degree of the numerator here is equal to that of the degree of the denominator. And for partial fractions, order for you to do partial fractions, the degree of the numerator must be less than that of the degree of the denominator. So in order for us to evaluate this, remember we're treating z to the -1 here as our variable. So it's easier to see if we just let some constant term here, m equals to z to the -1, and we substitute this in. So when we did this substitution and we transferred from h of z into h of m, we see here that the highest degree here is m squared on the numerator, and the highest degree is m squared on the denominator, which doesn't satisfy our partial fraction condition. So we long divide until we have the remainder satisfying the partial fraction condition, and then we just put the remainder divided by the original denominator, and then we just perform partial fractions on this remainder itself. So in evaluating this, remember the quotient here is just going to be by itself, and then the remainder here, you need to partial fraction this. So we factorize the denominator here, and we see that there's going to be 2 factors, so that means we're going to have an a and b constant here. And we can solve for a and b using our partial fraction formulation that we saw in our previous lecture. And then we can obtain the inverse Z transform by using the tables accordingly to get that. So in this particular case, a is going to be -21 and b is going to be +16. Now both the open form solution here and the closed form solution here, they are identical in nature. And I'm going to give you guys a little bit of homework. Try to figure out and do a little bit of research as to why the open form solution here, being the power series solution, and the closed form solution here are identical to each other. So if we plot the expected impulse response of this closed form solution here, we can see here that the poles here basically lie outside of that of the unit circle. Oh, wait, oops, sorry. This is a different example. My mistake. So for this particular example, we can see here that the poles here are outside the unit circle. Once the poles do lie outside of the unit circle, we typically have what we refer to as an unstable system. If we do the impulse response of this particular example here, you can see that initially our values are going to be 0, but then we go towards some infinite value here as we go up in samples. And this particular behavior is what we refer to as an infinite impulse response. And in analyzing this behavior, this is also what we refer to as the creation of an IIR filter, or infinite impulse response filter. And we'll be observing this filter design in a few lectures later on during the course. All right. So that brings us to the end of the the final Z transform lecture for today. Are there any particular questions regarding the material of this lecture? The impulse response graph, when you do plotting them, you'll have to use some sort of simulation software to plot this for you. If you're manually plotting them, remember you're going to have to substitute z equal to e to the power of g capital omega, where the x-axis here is going to be omega, and the y-axis there is going to be the amplitude or the phase accordingly when you're doing this. There's an associated command in MATLAB that allows you to do this for Z transform equations, but I'm going to have to research this accordingly to make sure what is the associated command for getting you the impulse response graphs in particular. But we won't ask you to manually plot these graphs. The information to plot those points are basically given from the Z transform equation that you had. So we'll have the Z transform equation here, and then we substitute Z here is equal to e to the power j capital omega. Transform this from h of z into h of omega. And then you plot for individual values of omega to get that impulse response graph. But like I said, we won't ask you to plot these graphs. This is just for evaluation purposes later on, like that's if you're trying to do some sort of filter design and you do need to see the impulse response. Typically, if you're using like MATLAB or some other evaluation software, there will be a command that you can just plug in the Z transform equation and it will give you the impulse response automatically. So I'm going to have to do a little bit of research to see what's the associated command for this in MATLAB for you guys to generate the impulse responses for any Z transform equations. Alright, any further questions? Okay, it doesn't look like we have any further questions, so let's move on to problem set 2A and questions that were associated with problem set 2A in particular. Right, so pull this down. Alright, so from the responses that we obtained from problem set 2A, the questions that we're going to be doing today are going to be questions 7, 8, and 9 here in particular, which gathered the highest amount of responses for problem set 2A. Alright, so cross back. Alright, nice. Okay, so let's bring up our problem set 2A. We'll do 7, 8, and 9. Right. Okay. I'm going to start with question 7 in particular. Okay, so bring up our whiteboard. Keep this working here for the time being. Okay, so this lines here, make the difference. All right, so we're in problem set 2a. The first question we're going to be doing is question 7. And we had our input sequence here given by this x of n. And we're going to have to compute the FFT of the sequence and identify the frequency components that signal had in particular. Yep. The first step that we do is that we're going to have to do the bit reversal process for x of n to set up for the input of our FFT. So step 1 here, bit reversal process. And we're going to set this up such that we have our x of n here. Given by our values, 0.944, negative 0.623, minus 0.532, 0.974, negative 0.12, minus 0.901, and 0.707. We then obtain the binary representations of each one of these positions in the x of n vector. So this here would be 0, 0, 0, 1, 1, 0, 0, 1, 1, 1, 0, 0, 0, 1, 1, 1, and we then reverse the first and last bits for the binary representations of each of the positions of these values. So the reversal here will be 0, 0, 0. So remember, we're just reversing the first and last bits in the binary representation. For this one, because it's 0, 0, 1, when we reverse the first and last bits, swap the first and last bits. This here will be 1, 0, 0, 0. Here was 0, 1, 0. This here will be 1, 0, 1, 0, 1, 0, 1, 1, 1. So our input here in the correct sequence for our FFT, by watching the binary representation here for our index of the x of n values, means that such that we know how to organize this accordingly. This be okay, what's going to be our input after we do our bit reversal process. So for the first input here to FFT, we look for the 0, 0, 0 value here, which represents 0. So that's going to be x of n here being 0. We then look for 0, 0, 1 here to match it back up. So we have 0, 0, 1 here, and the equivalent match here is 0.974. 0.974. We then look for 0.10 here. We match this back to 0.10. That's going to be minus 0.623. We then look for 0.11 and we do the match again. So 0.11 is here. Associated value is 0.901. Look for 100 here and match it up for the reversal. That's 0.944. Same thing as we keep on going for 1. 101 is here. Minus 0.12. 110. We need to match this back here to 0 minus 0.532. 111. The match is right here, so that's 0.77. Right. Verifying. Right, nice. So now that we have finished our bit reversal process, we can then move on to the decimation stages for our FFT. So we can move here to our first decimation stage. So the left hand side here of our first decimation stage is going to be the input towards our FFT here as a result of the bit reversal process. So I'm going to set this up here, such that this here is going to be 0.94 minus 0.623 minus 0.901 0.94 minus 0.112 or minus 0.532 and 0.707. Because this is here has been the first decimation stage, we need to set up a butterfly diagram accordingly for the first decimation. So because this is the first decimation, 2 to the 1, so that's 2 values. To be grouped. So for every 2 values here on the left hand side, we're going to be doing an associated butterfly diagram with them. So let's consider the first 2 values here being 0 and 0.974. And draw a line here accordingly for the first part of the butterfly. Next line here accordingly. And in the middle here, we're going to have a -1 block. Then we put our points here for the butterfly calculations. Draw the crosses here accordingly. And then we go about calculating these as required. So 0 here, we'll just transfer straight across. And then 0.974 here will go at this point and transfer straight across, and they just add together. So we get 0.974. 0 here, we reach this point and transfer straight across. Then we have 0.974 going straight across there. And that's going to be multiplied by -1. That's going to be 0 plus the multiplication of -1 by 0.974. This here is going to be -0.974. Similarly, we can do this for the other next pair of values. So we say 0.623 here will go across here, and then 0.901 will go across here as well. So in doing that, 0.623, because it's negative, minus 0.901, when we add the two together, we get -1.524. And then similarly here as well, we can have negative 0.901 multiplied by -1 here. And then we have this negative 0.623 coming across here as well, added. So this means here that we have negative 0.901 by -1, which is going to be positive 0.901 minus 0.623, which will give us a result here of 0.278. And we repeat the process as we keep on going for each pair of values for our first decimation stage. And do this one. Put in my crosses for the butterfly. This here will calculate out to 0.832 and 0.6. Next part here. Right, so this is going to be 0.175 and negative 1.239. So that will be the output of our first decimation stage. So then after we do this part, we take the output of the first decimation stage here, and we put this as the input to our second decimation. So second decimation stage. Equal 4 values grouped. So we take the output of the first decimation stage here, and we're going to put this as our input to our second decimation stage. 0.94 minus 0.9. 1.524, 0.78, 82, 56, 5, negative 1.239. And note the spacing that I have here in particular, because we'll be grouping every 4 values as required. Now, one thing to note in particular is that I know that this FFT here has 3 decimation stages. And the reason for that being is that the input sequence here had 8 values. And if we get to the closest power of 2 with that, that's going to be 2 to the power 3. So I know because it's 2 to the power 3, that means because that index power there being 3, we have 3 decimation stages. So we did the first decimation stage here. We're now at the second decimation stage here, and we're using each one of these decimations to know how to group our values accordingly to perform a butterfly. So when we evaluate for our second decimation stage here, because this is grouped in values of, because this is grouped here by 4 values, that means that the first value here needs to match with the third value, the second value here needs to match with the fourth value accordingly when we're doing our butterfly association. So within this grouping of 4 values, these first 2 values here will not have any total factors or negative ones associated with them. The next 2 values here will have total factors and negative ones associated with them. Because this is the second decimation stage and we're grouping by 4 values here accordingly, the total factors here, we associate them, are going to be W of 4. This one here is going to be W4 of 0, and this one here is going to be W4 of 1. We also know, because of the symmetric property of the total factors, are W4 of 0 equal to the minus of W4 of 2. So that comes like W4 of 2 here is equal to minus W4 of 0. That's why we have these negative ones here associated with the total factors to get the other total factors that are associated with the W4 here. So we can calculate for W4 0 up to W4 3. Right. So we can draw our lines going across here, each one of these values, to start formulating our butterfly diagram. And then we need to figure out, okay, which values here in this grouping of 4 need to match. So the first value here that doesn't have any total factors or any negative ones need to match with the first value that does have total factors and negative 1 accordingly to formulate this butterfly. So this here, oops, I'm putting the cross point at the wrong part in the diagram. So we put our cross point here for our first value that doesn't have any total factors or negative ones associated. And we match this to the first instance of the values that does have a total factor and negative 1 associated. And then we need to draw the next half of the butterfly here accordingly. And then we can calculate our values using these 2 values here for the output of the second decimation stage. So this 0.974 here is going to be going across here. And then we have negative 1.524 multiplied by W4 of naught going across here to be added to the 0.974. So this negative 1.524 here, because it's W4 of naught, if you remember your total factor equation, basically it's going to be Wn of k is equal to exponent of e to the minus g 2 pi k divided by n. If I remember the equation correctly, we can backtrack to the lectures to figure out what's the equation. You use this equation here to calculate for each one of the total factors associated, and you do the calculations as required for these in particular. So for this result here of the butterfly diagram, the end result here is going to be 0.5. And then for this second half here, there's going to be 0.974 going to negative 1.524 by W4 of naught, which is just going to be 1 multiplied by negative 1, so this becomes positive 1.524. So our result here is going to be 2.498. So this would be the first butterfly associated with these 4 values that were grouped. So then we need to move to the next butterfly to be drawn here in particular. So we watch the second value here that doesn't have any total vectors associated with them, and we match this to the second value that does have total factors and negative ones associated with them. So we put our butterfly cross point here. We're going to be matching it here to this. Then we put our next butterfly cross point here. But we're matching it this accordingly. So when we do the calculation here for this, this is going to be negative 0.974 going straight across here, then 0.278 W4 of 1 going across here. W4 of 1 is going to be minus g from a total factor values that we calculated. So this will result in negative 0.974 minus g 1.524. Oops, nope. Oh, I'm writing the wrong thing. Oops, my mistake. My calculations here. Minus g is 0.278. Alright. That's negative 0.974 going out across there. And we had 0.278 multiplying by W4 of 1. W4 in here was negative g. Right, so that's minus 0.974 minus g 0.278. Similarly, we have negative 0.974 here going across here. And we have 0.278 here multiplied by W4 of 1, which was minus g. And that's being made here by negative 1. That means it's going to be positive g. So this here is going to be negative 0.974 plus g of 0.27. So this gives us the first 4 values here for the second decimation stage. We need to repeat this process for the next 4 values here from the input to be grouped. So the process is basically the same thing. We can draw these across here. So the first 2 values here in this group of 4 will not have any total factors associated with them. But the next 2 values here will have total factors associated with them. Have a of naught and a 4 of 1 here. And we have our minus 1s here to map to other total factors. So in this next grouping of 4, the first value here must map to the first value with a total factor. So just repeating that, first value here that doesn't have a total factor must map to the first value that does have a total factor. Put our cross point here, go to the first value with a total factor, Similarly, put a cross point here, go to the value that didn't have the total factor, and then we calculate out accordingly for this butterfly as such. So 0.832 will go across here, 0.175 by W4 of naught. W4 of naught is going to be positive 1, so that's going to be the addition of these two values here. Give us 1.007. Then, because this is W4 of naught here, we multiply by -1. That means it's going to be -1 as a result of the multiplication of these two, multiply by 0.175. So that's going to be the difference of these two values, which will give us 0.657. We then draw the butterfly here for the next two values accordingly. So the second value here that doesn't have a total factor must match the second value here with a total factor. Cross point here. There's a cross here. A cross point here. Draw this across here as well. So this is going to be 1.056 going across here. Add -1.239 multiplied by W4 of 1, which is going to be -g. So it's going to be 1.056 plus g into 1.239. And then similarly for this part here, this is 1.056 going across here. And then W4 of 1 here being -g, multiplied by -1 will give us +g. That's going to be multiplied by -1.239. So our result here is going to be 1.056 minus g, 1.239. So that gives us the output of a second decimation stage. Now we can move on to the third decimation stage. Which is 2 to the 3, which means that's 8 values to be grouped. So we take the output of our second decimation stage here, and we put this as the input to our third decimation stage. So that's going to be 0.55 minus 0.974, J 0.8, 2.498 minus 0.94 plus J 0.78 0.7 1.56 plus J into 0.239 0.57 and 6 minus J into 39. Alright, so that's the setup for a third decimation stage. So a good indicator to know if you're on the right track when you hit the second decimation stage here is that these two values here, being the first and third value, will be unique in nature. Same thing here for the next group in here. But the second and fourth values here and the sixth and eighth values here just be where the imaginary terms are going to have different signs, and they will have the same magnitudes for the real imaginary parts. So for here, we had -0.974, which is the same thing here as -0.974, and the only difference between the two here is going to be the sign in front of the imaginary values, which was J 0.278. This here was negative, this here was positive. The same pattern was observed here, where we had 1.056 for these two values, and we had J 1.239 here was positive, and here was negative as well. So that's a good indicator to know if you're on the right track. If you don't see this sort of pattern, that means somewhere along you did the calculation wrong, so you won't have to review a calculation. So going to the third decimation stage here, because these are 8 values, that means the first 4 values here will not have any total factors, but the next 4 values here will have total factors. So we can draw lines here across calculations, but then for these 4 values here, we want to have associated total factors. And because it's 2 to the 3 here, that means n here is going to be 8 for the third decimation stage. So this here is going to be W8 of 0. This one here is going to be W8 of 1. This one here will be W8 of 2. This one here is going to be W8 of 3. And for each of the total factors, there's going to be associated -1. Going across points here. And similarly, when we're drawing our butterfly diagram here, we just match back the first terms, the second terms, the third terms, and the fourth terms accordingly. So, for example, so I just explained why the second row and the fourth row had a complex number because of these W4 terms here being the total factors. So this W4 term here being the total factor, remember this is the exponent form where it's going to be, alright, so this was Wn of k equals to e to the minus j 2 pi k divided by n. So when you evaluate this accordingly, when n is equal to 4 and k is equal to 0 and 1, in the total factor form, this here is going to be W4 0, this here is W4 1, this here is W4 2, this here is W4 3. And in reviewing the lecture on the total factor, you know that all of these here are going to be magnitudes of 1 for the rotating phasor. So this axis here is going to be the imaginary, this axis here is going to be real. So this one here for W4 of 0 is going to be 1, this here is minus j, minus 1, and this is positive j. So you can get that from evaluating the 12 factors here as well. And once you evaluate those 12 factors and you do the butterfly calculations, you see that's why we do get imaginary values associated with them. Alright, so going back to the third decimation stage here, in drawing out our butterfly diagram, we do the same thing as before, but now because there's 8 values to be grouped, the first 4 values here don't have total factors, and the next 4 values here will have total factors associated with them. So the first value that doesn't have a total factor must match to the first value that does have a total factor to formulate the butterfly. So cross point here, next cross point here, do that, same thing for the second one. Cross point here. Third one here. Cross points. Fourth one here as well. Alright. So that basically concludes how we go about drawing for the third decimation stage. Now, the nice thing about this is that we don't need to do all the calculations here for this third decimation stage. We can actually use MATLAB, and it can actually calculate out the output here for the third decimation stage as required for us. I'm using Octave Online, but you can use MATLAB as well. So if you remember, our input sequence here was given by the sequence of values here. Hopefully it cooperates when I paste it into my browser. I can say x is equal to this. It doesn't incorporate because I have a comma somewhere inside there, right? But still is incorporating. Oh, because I have spaces. See if I can get this to work here properly. Alright, there we go. So I have my x vector here from the question, and I can just call FFT of x. I'll get my end result here as required for my FFT of the entire signal. So because I have the end result here, I can just put that end result in accordingly onto my diagram. So the first value here is going to be 0.5457. So out a little bit here. So this is going to be 0.457. Back here, our next value was 0.6488 minus 0.1486i, so I'm just going to round that up to 3 decimal places. So this is going to be 0.649 minus g, 0.149. All right, verify that. Yep, all right. Our third value here was 2.498 minus 0.657i, so I'll just put that in accordingly. J67. Fourth value here was negative 2.5968 plus 0.47074. Like I said, I'm going to round this up to 3 decimal places. There's going to be minus 2.57 plus J 0.407, and we basically just keep on doing that for each one of these values here to finish the third decimation stage or the FFT of that X signal. So this is going to be negative 1.557, negative 2.597, minus J 0.47, 2.48 plus J 0.57, 0.649 plus J into 0.149 here. And that basically will give you down to the end of the FFT equations as of such. Now, there's one thing to note as well when you're doing this particular type of question before I get on to what's going to be the frequency component part, is that when you're doing these questions, you are required to calculate out the total factors for each one of these. Now, you don't need to calculate these out manually. You actually can use MATLAB or Octave here to actually calculate these for you. So in this case, where we have W4 of 0 and W4 of 1, we know the equation for the total factors is Wn of k. So I want to show you guys a very quick way on how to calculate for this. So let's say n here was going between 0 to 3 because it's 4 values that we're going to be calculating for. W here is equal to the exponent of minus j by 2 pi by n. And you can see here that W here will calculate out all the total factors for us. So just to keep with consistent with us, W is that. Check back my equation here just to make sure it was correct. Okay, 5 by 4. Right, nice. Like I said, n here is equal to 4, so I can remap my equation here to match. Okay, good, nice. So what I did here is that I said n here is equal to 4 for the first decimation stage. Sorry, for the second decimation stage. this in a little bit. And then I said k here goes from 0 to 3. The n here is 4, k here is 0, 1, 2, 3. And then our total factors are equal to w exponent of minus j by 2 pi by k divided by n. It calculates all our total factors here for the second decimation stage. So you see the first one here was 1, second here was minus j, third one here was negative 1, fourth one here was minus, so positive j here accordingly. Similarly, for the third decimation stage, when we add up to w of 8, all we need to do now, because we have it already in our MATLAB or Octave code, is to just change the values of n and k accordingly and just map it back to the total factor calculation. So for the third decimation stage, remember n here will go up to 8. And that means k will go from 0 to 7 instead. W, you just call back the W equation here, and you will get all the 12 factors associated for your calculation. And if you want to call a particular W value in this vector, we can say W of 1 here, and W of 2, W of 3, and so forth as you keep on going. W of 4. So if you see like some weird values popping up here, just ignore that. Because these values are really small in nature, the compiler just gives you like a rough estimate, and this is because due to the hardware the compiler uses in the background for Octave and so forth. So you don't need to worry about that too much. It's actually the correct values here that you're seeing, so don't worry about it too much. W of 5, and we can keep on going and so forth as we have it regardless. Alright, so let's say if we did want to do one of these calculations here, we have negative 0.55 here for this. So we say here minus 0.55 plus, and this here is 1.007 of W8 of 0. So here 1.07 by W of 1. You can see here this will calculate out 0.457 for us accordingly. Similarly, let's say if we want to do it for the second one here, so this is negative 0.974, negative 0.974 minus d by 0.278. Add 1.056 plus d by 1.239 multiplied by, we have W8 of 1 going up here. So this here being W8 of 1, that's going to be W2 because of the indexes. Probably didn't complete a bracket. Get this back to where it was. Right. You can see here that it calculates out our answer as first accordingly, which matches back to what we had. 0.6488, which I rounded off, minus 0.1486, which was 0.149, accordingly as of such. So when you're doing this particular kind of question in particular, you want to make sure that you do calculate out each one of the total factor values, because they are worth marks, as well as you want to make sure that you do your calculations here correctly for each one of these. And yeah, I'm not watching the time, and I realize I did go over time, so I'm just going to complete this question and we're just going to close off at this point in time, because I really have gone over time, so I do apologize for that. Right, so the last part of this question was asking to identify the frequency component. And the frequency component here, because we had 8 values, and we had the sampling frequency to start with, f of s here was 280 Hz, and here was equal to 8, so we calculate for the bin spacing, which was 280 divided by 8, was 35 Hz. And then when we watch our values here, the values that do have a very close similarity are the third and fourth values here, which represents where our frequency component is going to lie. So this here will be at 0 Hz, this here will be at 35 Hz, this here will be at 70 Hz, and this here will be at 105 Hz. So this is 0 delta F, this is 1 delta F, this is 2 delta F, 3 delta. Because these two values here are very similar, that means because it's on the line between signal lies in between 2 delta F and 3 delta F, where that is going to be 70 and 105. Alright. Yeah. I do apologize for going over time because of the question. I know some of you guys may have some classes, so I do apologize for that. Right, so in answering that last question there in the chat, the number of decimation stages will depend on the number of values, yes. So because x of n here had 8 values, that maps to 2 to the power 3. And that 3 here means that there's going to be 3 decimation stages. If for some instance, like let's say if this was 7 values, you need to go up in values to the next closest power of 3. So closest power of 2. 2 above 7 is going to be 2 to the 3, which is 8 values. And once it's 8 values, you just add a 0 onto the end of the x of n signal to 0 pad it, and then perform the FFT accordingly. Alright, so I will post up the solutions for problem set 2a. I know we didn't get around to doing the other problems as well. I will see next week if we can go about doing problem set 2b in particular, any particular questions regarding those once I finish the lectures early. So I'll do that on next week's Wednesday session in particular. If we do finish a little bit early on the Monday session as well, I will do a little bit of the problems as well, problem set 2b as required. I will basically give you guys some ideas on what sort of things to expect on the midterm or from next week, but basically I can tell you that the topics you're going to be tested on for the midterm is going to be up to the end of lecture 8. I'm repeating that, the topics you're being tested on the midterm is up to the end of lecture 8. But next week in particular, I'll give you guys a little more preparation as to what you want to expect on the midterm and so forth, and how it's going to be formatted and whatnot. Alright. So next week's lectures are going to be on transfer function realization and the start of digital filters in particular. So again, I do apologize for going over time today. Hopefully we won't go over time again for the rest of the course. And I said I'll post up solutions for problem set 2A. I'll also post up solutions for problem set 2B, but in next week's sessions I will go through some of the stuff in problem set 2B as required. So until then, take care, be safe, and I will see you guys soon. And if you have any questions, leave them down in the comments below or directly email me. Alright, so I'll see you guys soon. Later.